just as you're drinking your coffee. Hey, Graz, thank you for being here.
My pleasure.
So I remember we met when we worked at Synack together, and we worked on some really cool tech. And I would say, you know, if I was to kind of think of all the hackers out there, you're probably like one of the smartest and most talented hackers I know of. And so I'm hoping to pick your brain a little bit. So since then, you kind of moved on to work on cars and work on that technology. Can you talk a little bit about that? Like, how did you end up working on that cool stuff?
Sure. The way I like to describe it is that I kind of stumbled my way to what you might call success. I kind of like TikToked in different directions. For example, I started in embedded as a developer. I worked at NVIDIA and I worked on Android platform stuff. And that makes sense because I was always interested in how things worked. And I was kind of want to like drill through the abstraction layers and understand like as low as I could. And obviously working on firmware was pretty damn low. So that ended up helping me later on. But while I was doing this, I always had been interested in security. And the short version of the cool story for Synack was that I decided to go to DEF CON on my own, and Synack was giving a presentation, and I thought it was super, super cool. It happened to do with hardware, which was even lower than what I was used to working on. And I had like reverse engineering, just everything that was interesting to me. And I talked to the people who presented, Colby and Patrick, and I literally said, like, I'm going to apply to this company. And I did. So that was my first foray into security. And that's when I met you and a bunch of really cool people. And I honestly had an awesome time. And I wasn't doing security like research or anything per se, but I got to work with a bunch of really good security researchers, excuse me. And it was like an awesome opportunity to learn. And around that same time, I started CTFing. And it was just a way to do some security stuff on the side that, again, turned out to help me a lot. But it was just my interest that drove me. But then I got tired of Synack, and I was really interested in Tesla as a company. And this is kind of where like the first bit of luck. Synack helped because, I had been doing some security stuff. CTFing helped a ton because I was doing like binary exploitation, reverse engineering, which Tesla was particularly interested in. And then like the best coincidence ever was that their vehicle was using an SoC that was developed by NVIDIA that I had worked on at the start of my career. So they had some questions about that during my interview that I nailed. I was like, I already worked on this stuff. So that was just like serendipitous, and it got me into that. And turns out that I get to work on embedded stuff. I get to work on security. I think it's impactful because it's pushing EV and it's pushing self-driving. So I think it like has good impact on the world. And it's managed to keep my interest. So I don't work at Tesla anymore, but I decided to stay in the field, and well, that's where I am today.
It's pretty fascinating how you mentioned that your security sort of track and practice got merged with some of your history in embedded systems development. Is that kind of the layer you stay at right now? You're working on embedded systems, but more from the security side.
So I'd say I moved a little bit higher up in the layers, because when I was working in NVIDIA, I basically worked on like bare PCBs. And while I still work at native level, I do write some kernel stuff. It just happens that a lot of stuff I work on are server grade x86 machines. We just happen to shove them in cars. But from the perspective of a developer, a lot of the constraints are gone. I'm not worried about, under a gig of RAM. It's like we have 64 gigabytes of RAM on these machines or so. Like they're big, powerful machines. And we're developing in Go, and we have SSH and all these things like that. I don't have to worry about like power trees and things like that. So I think having that sort of understanding is still super helpful. I think that's just true in general. But I don't have to worry about it as much, just because the constraints aren't there so much.
Yeah, I mean, working without constraints is, well, not without constraints per se. I mean, you still have the constraint of this is just a computer, and you have to worry about the software stacks involved in there. Where would you say is the most interesting layer of abstraction that you prefer to work in? What are the unique challenges in there?
Well, I'd say that changes over time. I would say, to answer the question, the most interesting abstraction layer is whatever one I'm interested in at the time, because I think it's so fascinating. And then I kind of like crack through it, and then I go, oh, you know what? Like, that's boring now. And I go to another abstraction layer. I tend to prefer lower level ones because I just think that it helps me understand what's actually going on. And I've gotten over this attitude, but I remember I used to like almost think condescendingly, I don't anymore, to like front end developers, because I was like, they don't understand what is happening below that abstraction layer. But even I definitely shed that when working at, if you think of like Meltdown and Spectre, even people who understand what's happening at the machine instruction layer actually don't know what's happening, because there's so much deeper beyond that. Obviously there's like the electrical engineering, but now with x86 machines running like microcode, it's like you run an instruction, there's a ton more happening there. So now I just think that the whole stack is interesting, and just knowing kind of what's around the boundary is both valuable for security reasons. Meltdown, if you stay at the abstraction layer of CPU instructions, you would never come up with Meltdown. The only reason people figured out that vulnerability is because they wondered what happened underneath it. It's a leaky abstraction sort of thing. And I think, go ahead.
Sorry, can you dive in a little bit on the Spectre Meltdown situation? What is the thing that was happening there, and why was it a vulnerability?
Sure. So I might get some of the details wrong. I haven't thought about it too much lately, but the main idea is that x86 or all CPUs now have a ton of hardware now to optimize. And what x86 is doing was they try to prefetch memory, and they have the way that they get these speed up increases is that they prefetch memory and instructions way ahead of time. And the main idea is, if they make a mistake, they just throw all that information out. But because they often get it right, then they have the benefit of having prefetched that stuff, and they, hey, it's already ready. So what's happening in Meltdown was, it was a side channel where you could trick, or for another background, if it were to prefetch memory, but it was not allowed to because of like security levels, it would throw that out. But it would still prefetch it. I forget if it was because it didn't know at the time, but the point being is the design was supposed to be secure because it wouldn't actually allow that memory to be copied into memory that could be read by the program. But the side channel was that you could infer what the value of that memory was based on the timing of how long it might take to hit another like memory address. And this basically had to do with whether like the cache was hot at a certain like page offset, and you could trick it into like if some page offset was faster by some amount of time, you could infer that that value that they illegally read matched that page offset, and you could just leak bytes out. And again, if you're just trusting that all the instructions you're running at assembly are happening and only those instructions and always in order, you would never think of this, because it just throws away that assumption.
So how deep does this stack go? I mean, see, you have instructions. Most people tend to think of that as like, well, this is the machine. There's nothing below that. This is just the CPU executing my stuff, and you can trust the hardware to do this for you. How deep does it go before it gets to the electrons?
Yeah, well, that's the funny thing is, because before the instruction set itself is an abstraction. 30 years ago, it was basically all that was happening. There's obviously, it's built out of circuits, but the instructions did just happen in order. And these instructions exist for a reason, right? They exist so that we don't have to worry about that kind of thing. And they make it simpler. So like that web developer or whatever that I was talking bad about, he or she can be productive because he doesn't have to worry about all the layers underneath. To answer your question though, I don't know how deep it goes. The way a lot of processors work now is there is an instruction that is implemented that executes a CPU instruction. But in modern day CPUs, that is actually executed in something called microcode, which is actually itself reprogrammable. And I don't know if there's more layers than that, but that itself is implemented in hardware. Instead of just implementing, let's say, an adder or let's say a compare and check with simple hardware, you actually implement it with a smaller, more efficient CPU. Underneath that, I hope, maybe it's turtles all the way down, but that's where you get like the logic gates and everything.
Yeah, that's fascinating. I mean, at some point you must get to the transistors where the actual logic gets executed.
Of course.
It just has to be. Otherwise, turtles all the way down is just software. Then nothing gets done.
Yeah.
I remember, it's interesting you bring that up, because I remember when I was studying software at this level, and it always ended with instructions. And then one day I saw a job post at Intel that says, we need offensive security people to look at microcode for the Intel architecture. And I just thought, wait a minute, this is just more and more abstractions, and then there's software keeps going down, even though it looks like hardware executing and stuff. So it's real, and it's quite fascinating.
Absolutely.
So okay, so let's when I think of cars, right? Like if we go back to cars, when I think of cars, effectively today they're like giant computers on wheels. I mean, wheels are just another hardware to them, and they can operate it. But when I think of computers, I just think of all this code out there. It's buggy, it's vulnerable, it's written by thousands of engineers, different layers of competence. What do you see as some of the interesting challenges for sort of protecting those machines, specifically around binary analysis, binary exploitation type attacks?
So one of the things that like a starry-eyed engineer or security engineer usually thinks is like, secure everything, make sure there's no bugs everywhere, anywhere rather. And, ideally that's true. But like you said, there are billions of lines of code running on the vehicle. There's code running in the seat controller, in the tire pressure monitor. Every button is connected to some computer. Something is reading from the sensors. The sensors themselves have computers that have to like package the data into whatever format. Like how is it getting it from the sensor on, let's say, the roof to the part that does all the number crunching?
So this isn't just one computer even, it's like multiple computers.
Absolutely. Yeah, many computers. And so anyways, you can't make that perfect. So the most important thing is threat modeling. You have to identify where the risks come from. So for example, the tire pressure monitoring system is a computer, and maybe it can talk to the main computer. Is there a path there? So what you do is threat modeling. You basically figure out where the inputs are, and you focus on the ones that are user controlled. Your threat model might say, hey, in my Tesla, if I have one, an attacker could open the trunk or the frunk or whatever and access things, and might be able to like gain physical access. But in a more lockdown car or a car that they don't own, the threat model might change, where you go, oh, they only have the opportunity to interact with this through the app or through the physical console or through the tablet, right? And by making these threat models, you identify which parts are the most vulnerable, and you focus on them.
Interesting. And is there a lot of people attacking these things? I mean, what am I worrying about it?
Right. I mean, I wouldn't worry about it per se. Tesla, Cruise, a lot of these companies, like it's a pretty well-known thing now, and they're putting the resources in. Are there people attacking it? It depends like what the goal is. Are people hacking their Tesla to say that they hacked it? Absolutely. It's a ton of fun. Are people hacking their Teslas to unlock extra features like I forget what it's called, ludicrous mode and things like that? Absolutely, or at least they're trying. And that might not even be as important. Now, then if you get into the question of, are nation states trying to hack Teslas so that they can take over? I don't know. I certainly hope not. But that is in part of your threat model. It might be less likely, but also you have to consider not just the likelihood, but also the effect, the damage it can cause the affected users. If it's self-driving cars, loss of life is obviously a terrible thing to consider, but you need to.
That's interesting. So you're almost in that threat model. You're almost also protecting against their own users, right? You don't want me as a user of Tesla to say, well, I want to change the car because I can get through the software.
Right. So again, it depends what you want to focus on. Let's say you make a video game. You don't want people to hack to ruin the experience for others, but also you don't want people to hack because you want to sell hacks or whatever it is in whatever game. So yeah, you might want to, there's different incentives. For self-driving, again, there might be the incentive to not get free rides or something. But I think for the most part, the big incentive is don't kill people. And let's get—
pretty good incentive.
Right, absolutely.
How do people interact with these to create hacks? Is it just through some kind of a special port? Is there Ethernet port on these?
Yeah, so like to get back on the threat modeling thing, and you mentioned binary exploitation, which is like where I like it the most. I find it most interesting. So for example, in the Tesla, you have the center console. That is a opportunity to enter input, right? And I can't give too many details of how it was when I worked there, but it's obviously running some operating system. And there are paths through whatever UI into, like, let's say it's through a browser. You might be able to escape that sandbox because the browser is obviously going to be sandboxed and provide your input directly to some daemon running on the machine. But also you could just open it, and there's, like, let's say the instrument cluster, and there are Ethernet cables. They're not like the normal RJ45 you might expect, but there are ways to just plug in directly. And then there could be whatever service is running there. There could be like SSH, and maybe just running a vulnerable version of SSH where it's just like some 0-day, or again, because it's more difficult to patch vehicles and things like that. Maybe it's not a 0-day. Maybe they're just running old versions of OpenSSH or whatever they're running.
So it's just a matter of, well, make sure your stuff is up to date. I mean, that's a story that goes through almost every computer out there.
Right. I mean, of course, it's make sure your software is up to date. But of course, there's not a lot of, hey, here's open source car drive software, right? So they also have millions of lines of their own software. And the fact of the matter is, like, your inputs have to, let's say in the case of a Tesla, your inputs have to somehow make it to the wheels, right? Because you control the vehicle, even if it's by telling it some input. So there is some path through there, but by constraining it, so that, for example, through the display, you can't control the wheels directly, but you can only talk to some, let's say, mapping module that will talk to the powertrain and the brakes and everything. You can constrain what data can go where. And then you can focus on, for example, firewalling or isolating. You know, like the basic principles of security, and it's like to isolate and least privilege. So if you have a display, maybe the display shouldn't be able to have an accelerate button on it, but of course the gas pedal does have to, right? But by having the gas pedal focus on only acceleration, you can make it so that whatever messages are coming from the display never allow an accelerate message to be either accepted or even passed through.
I mean, you're almost describing a networking diagram here. I mean, it's things are in DMZ.
Absolutely, cars are just networks of computers.
That's really cool. Yeah, I mean, I remember in 2018, I think it was, at CanSec West conference, there was a Pwn to Own for Tesla. And some team, I don't remember where they were from, some team hacked into a Tesla. And when I say hacked, they had some kind of a browser exploit against Chrome browser. And, you know, they were able to escape the sandbox And then from there, from the infotainment, they were able to bypass some other security mechanisms and actually get into the control for door locks. And they were able to unlock the car that way. I don't know exactly all the steps are, and I'm sure a lot of it is very proprietary, but it's super fascinating how that can even work.
Yeah, absolutely. And that's like kind of the same thing with iOS. Like, not only is it just getting one exploit, if you tear apart the car and you find an exploit in the kernel of the self-driving module, that's awesome. But if you want to hack a car on the road, unless you also tear it apart, it doesn't get you much. But if you can exploit the browser, and then when running that exploit in the browser, use that to pivot and basically dig deeper, another reason why this networking illusion works well. You're chaining these exploits together. And the best one, let's say with an iOS one, is where they say if you have a touchless route where you can just send an SMS and own their phone rather, like that's ideal. Similar to the Tesla one, I think I'm thinking the same one as you had to trick them to connect to a certain Wi-Fi and then navigate to a certain website. And it would exploit the browser, escape the sandbox, exploit the kernel on that machine, and then communicate or pivot to another machine and then control it from there. So that is a nice chain of exploits and very valuable.
That's very involved. And I suppose these, I mean, we talked about Chrome. Chrome exists on Windows, Linux, and Mac and other operating systems. I mean, does that mean that effectively this machine just runs the same desktop I'm using to record this, for example?
Well, I mean, I don't think a car is going to be running Chrome in particular, but they do leverage, a lot of vehicles leverage a lot of open source things, whether it be WebKit or Linux. So there are definitely cases where vulnerabilities in the wild apply to whatever consumer hardware or even vehicles.
Very cool. Okay, so let's ask you a little bit of something else. How do you get across these skills to solve these challenges, these hacking challenges?
Practice, right?
Yeah. Just practice. Like, I mean, well, let me ask you slightly more coherently. Like, how do you develop these skills? How do you actually practice? Like, what do you spend time working against capture the flag challenges? Do you have some kind of things you like to repeat every day, or anything else, like where you read your information?
Yeah, so I'm doing less offensive security now than I used to be, but I definitely was pretty literally drilling a lot of exercises. It depends, like there's always a trade-off of like broad knowledge and deep knowledge, and there's only so many hours in the day. But I am quite a believer in practice makes perfect. And if you know what you want to work on, then just practicing those things is really good. Going back to the trade-offs though, you might want to like dance around and try different things. So for example, I knew pretty early on that I don't really like web exploitation, but I like reverse engineering and I like binary exploitation. That shrinks it down quite a bit. But within there could be like malware. There could be malware on different operating systems. There could be like game hacking. There could be like hacking daemons. Reverse engineering, like a lot of CTF challenges now are reverse engineering Linux binaries or exploiting Linux binaries that use libc, and half the vulnerabilities are some issue with like glibc's heap and the different mitigations. I would actually warn that focusing on that too much might have limited real world applications, but I absolutely would go on like challenge websites and download a bunch of challenges and try to hack them. There's a bunch of glibc like house of something well-known vulnerabilities, and I would explicitly practice each one, and I would practice challenges that I knew had heap vulnerabilities, but not which ones, so that I was better able to pattern match an off-the-shelf exploit, or an off-the-shelf exploit to this particular one. Some challenges where it didn't exactly fit in the model, like wasn't exactly House of Orange or whatever. And then I even did things, if you're doing competitive CTFing, less valuable to the real world, but not useless, literally like drilling for speed. Things like throwing something into IDA or whatever disassembler you prefer, and trying to find vulnerabilities as quick as possible. My CTF team, we used to have competitive speed hacking where it was like heads up, two people trying to exploit the same binary at the same time. And people, and now that I know they do that on YouTube, but we were first. And it does get you the skills to be faster, absolutely.
So you just pick a challenge and then you start working on it, and you try to race against time to solve it as quickly as possible.
Yeah, I don't think race against time is the most valuable thing. I think the most valuable thing is to continuously try more difficult challenges. It's really easy to, well, one nice thing about CTS is they often have point ratings. And it's really easy to do, hey, I'll do all of the Pwn 100 challenges, assuming they're all about equivalent. I would actually say that's not a good idea. You might get really good at Pwn 100 challenges, but then you might be completely stumped when there's a 300. What I would actually suggest is do a Pwn 100, try a Pwn 1000, probably fail, and then kind of like binary search within there to find the hardest challenge that you can solve, or maybe you can't, but the hardest that you can make progress on, and try to solve that. Because if you're just practicing easy things, you're going to get really good at easy things. I think it's better to push it and basically level up your maximum over optimize for the low end.
Do you remember what are some of the technical differences between the, let's say, Pwn 100 and Pwn 1000 challenges? Like what do they try to exercise from you?
Yeah, absolutely. So CTS have definitely gotten a lot more difficult over the years, which is a good thing. It just means that the whole industry has leveled up. Back in the day, like easy Pwn would be something like a pretty simple buffer overflow. And then as the difficulty goes up, they'd add more mitigation. So for example, they might add stack canaries, or they might add ASLR, or they might make it more convoluted in its implementation. So for example, they might do input filtering, or they might make it so that there's just a bunch of restrictions on length, or just things like that. And then as they get even more difficult, it can be like timing issues. It can be, what else can it be? Timing issues, really convoluted. Then it can begin to like heap exploits. A really common one now that I like a lot is a lot of them are like sandbox escapes from VMs. They might be on like weird machines. Might be ARM, might be MIPS, might be PowerPC, might be RISC-V, might be like chip 8, which is like a fun fake machine. I actually like those challenges a lot. And then of course, any combination of these. There can be some crazy one where they implement ASL. Actually, a really, really fun one I remember was on something called microcorruption that Monsanto, when it existed, or Matasano, not Monsanto.
Monsanto. Monsanto is a corn company.
Yes, easy to mix up the two. Anyway, where it had you exploit a bunch of things on MSP 430. And one of the more difficult challenges at the end was actually ASLR. You'd read they provided a debugger, and it worked for all the challenges. But on this later challenge, it would get a random number and then relocate all the code in it and implement a VM. And its own code broke its debugger. So basically, the harder challenges, you couldn't use their own tooling. You had to like write your own tooling.
So the challenge there is really like getting up to speed with the architecture, getting up to speed with the tooling, and then applying those same mechanisms that you've seen in, let's say a more normal architecture, but in this environment.
Yeah, absolutely. I think a really, really valuable skill is pattern magic, is trying to identify, whether it is by looking at a graph of disassembly and be like, oh, this is whatever algorithm. Doing that quickly, or just being able to do it ever is super, super helpful, because it lets you pull up a corpus of knowledge, even if it isn't yours. If you go, oh, I recognize this as a VM protect escape, that gives you something to Google. So that's super, super helpful.
That's really interesting. Would you say that, I know you said you don't really do this as much as before, would you say that these helped you professionally to kind of develop the skills you're applying now?
Yeah, absolutely. The funny thing is that, again, I'm not doing stuff as offensively now. I'm not doing as much reverse engineering, but there's times when people, for example, we had to work with some binary that wasn't working to spec. I'm talking like really obscurely. And I could figure it out before everybody else because they're all reading through the documentation. And I go, let's see how this really works. And I pop into disassembler and go, oh, they didn't implement it correctly, right? If you trust the spec and they don't implement to the spec, then it's not going to work.
So effectively, those skills allowed you to get to the source of truth quicker than anyone else because you don't have to rely on the documentation.
Absolutely. I love my reverse engineering school skills for debugging is I wouldn't trade it for anything.
That's very cool. What's your tool set? What do you like to use?
So it depends. I like doing a combination of dynamic and static analysis. There's Ghidra and Binary Ninja and Hopper and a bunch of really good tools. But I'm lucky that my job pays for IDA Pro, and I'm most familiar with it. So I use IDA Pro mostly and GDB. And then
cool.
To be like a bit of a shameless plug for GDB, because when it's compiled with Python, I work on a bit of a framework that makes it like 1,000 times nicer called GEF, GEF, and it's just makes your life so much easier.
Well, tell me more about it. I mean, I like this plug. Tell me more about this framework.
All right, so it's github.com/Hugsy/Jeff. I'm not Hugsy, but I just found it, and there existed something back in the day that was just called GDB init, which is poorly named, but it just replaced the normal GDB init RC. And what it does, and this is just expanded on it, made it very nice. What it does is if you've used vanilla GDB, you're given a little prompt and you can say like, inspect this register, step instruction, whatever. The biggest thing that this does is it gives you a nice display of what you're looking at. It can show all the registers, it can show the disassembly, it can show the stack. It does like nice color coding. So like when you're stepping through, it'll highlight which registers changed on that step. And then it adds a bunch of like, a bunch of good quality of life things like create a De Bruyne sequence so that if you can get a segment of the sequence put into a register, you can detect or you can calculate rather what offset into the sequence it is. And that's good for calculating the length of a buffer that overflows. And things like set breakpoints on all format string functions and auto detect if they use user input as a format string. And it basically just tells you for free if there are format string vulnerabilities. And copy this code and write a Python file that uses Unicorn to emulate it. And that way you can poke it and like inspect it at every point in time. And just a ton of really, really nice things.
That's very cool. You're gonna make solving easy challenges too easy because all these cool tools are available and to expedite your experience. I mean,
that would be true.
Yeah.
That would be true, but easy challenges are getting a lot harder.
Okay. So you're forcing the industry to level up by creating better tooling then.
I'm not sure if I'm the forcing function, but I'm definitely trying to like move along with it.
Yeah, that's very cool. I don't think that in this class we talked about Jeff, but I think this is something we're gonna put in as well. I think Pwning Tools is the one that's a go-to for a lot of
Pwn Tools is absolutely like I can't live without it. And another one, I use Pwn Tools sometimes for debugging random things. If I have to talk to a random service, like I'm not exploiting the service. It's just nice to have a nice library that I can script with triggers a communication or like a conversation with it.
Oh, that's interesting. So you're actually using these tools not for security analysis. You're just using it for analysis of the software itself to understand how it works so that you can develop against it.
Absolutely. I find the tools useful way beyond just exploit development.
I didn't think about it. That's really cool. Well, what does your workflow look like when you are solving these challenges? What sort of like tips and tricks that you end up finding on the internet? Where do you look for them if you do?
So I happen to be part of a big community that hangs out on Slack, is just our CTF team, open to all. And there's a lot of good discussion there. Just you join the channel that has whatever you're interested in, and links are bound to be posted. And you know, if you're interested in it, you'll also find it out. I really like reading write-ups for CTFs, even if I didn't play them. But if I did play them too, even if I solved it, you can look at different approaches and learn a lot from that. And yeah, just like if you're interested in it, you will find the things and just read it. And then for my workflow, it depends a lot on what I'm attacking. But like again, the typical Linux binary using libc. I used to use a VM, but I actually now mostly do everything in Docker. When it works great. And I just have a bunch of scripts that make it easy. I have a Docker open in a terminal, split up with Tmux, and I have IDA Pro sometimes connected to Jeff. That's another thing that Jeff can do, is it can like highlight your breakpoints in IDA and basically have a Vim window open with my exploit that I'm writing, and another one that I keep running the exploit. I have a script to open the debugger, and basically just everything is in front of me. It doesn't take long to switch between the two, the script, the execution, and the analysis.
Mm-hmm. So Docker is the thing that actually executes your target, and then you can iterate really fast by just having it in an isolated environment.
Yeah, and then a lot of times people have like some VM that can run this stuff, but something comes, some vulnerability or some challenge, and it has some weird requirements, and they install all these things. Then the next CTF comes, but they trash their VM from the old one. And you can use snapshots, but to me, I just like my Docker's headless. I do everything in the terminal, and you just kill it and start it again, and it is clean slate. So I just have a Docker that I make my own that has all the tools I need, and like basically nothing more.
That's very cool. Well, what do you do if you know, if you face a challenge? I mean, real world or CTF challenge, and you just don't know how to approach it, like you don't know how to solve it. How do you go about, you know, trying to understand it better, trying to make breakthroughs and ultimately solve it somehow?
Mm-hmm. So yeah, definitely one of the like crappy things is if you take a challenge that you have no chance of solving, it can be really discouraging. And on my CTF team, I see it happen quite a lot. Another problem is if like some of the newer guys do try to solve a challenge, and the more experienced ones solve it in 2 minutes, then that also can be discouraging. But I'll say that the people that I see succeed the most are not necessarily the smartest. They're absolutely just the most tenacious. It's not always good to just bat your head against a problem continuously until you solve it, but it works a lot. So you don't want to choose a challenge. Like for example, if you know you've never solved a 500 level challenge, and maybe don't go with that right away, especially if you're doing this like competitively. You kind of like have a ballpark where you're going. But in general, if something's difficult, like keep at it. I think tenacity is super important to make progress on it. As I mentioned, being able to pattern match is very valuable. If you go, oh, this is clearly a heap exploit. I know of these different common heap exploits. You can pull these up. Whenever I do a CTF challenge, I end up opening 35 tabs with random things. A lot of, yeah, it's a mess. And then you're done. Then you have to close them all. But it's just knowing, just through experience, you kind of learn what to look up and like how to do your research. There's another pitfall that I find funny. I call it CTFering, and it's where you are so used to CTFing where you're not actually doing real world stuff. So for example, if you get a binary and it's like gigantic and it has some small library that they wrote, you just go, oh, the vulnerability is in that library. There's no way they would make you reverse engineer this gigantic thing, right? In the real world, that's not how it works. So that's actually good for CTFing, not for real life. And I actually literally do find that kind of thing a problem in my day-to-day sometimes. For example, in auditing code, in CTFing, it can be a bit more encouraging because unless the CTF is very poorly done, there is an exploitable vulnerability in there. But if you're auditing code or trying to find it in real world software, it's not necessarily in there. But some other good advice I got was, there is a vulnerability in there. Just, there probably is.
Just
And
pretend like there is one.
even if there isn't, pretend there is. Yeah. And then that kind of goes back to that tenacity I mentioned. If you train that, I think you'll be able to make really good use of it in real life.
Mm-hmm. Yeah, that's a fascinating thing to have to cross. It's like a bridge you have to cross, where once you've gotten good at solving CTF challenges, the real world environment is slightly different. And for me, at least, the biggest difference I find is what you mentioned, is that when you start looking at a piece of code, there might be 40,000 millions of lines of code. And there is a bug somewhere in there, but any particular component you're looking at, you don't know if there's a bug there. And you have to kind of know when you've looked enough and when you sort of should stop and move on. So can you maybe give some thoughts on like how if, let's say you're working on a CTF challenge and it's too hard for you, how do you know to stop? And in the real world, if you're looking at a component, you're doing some source code auditing, how do you know when you should stop and move on?
Yeah, good question. And one that I probably don't have the best answer to, because I don't think it's my strongest skill, unfortunately. I will say that just in general, you get a better feel for it. In the CTFering vein, one of the ones is, it's a 200 level challenge and you've spent this much time on it. Either it's too hard or you're looking the wrong way. In real life, what I like to do, I don't do auditing anymore, but what I did is kind of like time box it and go, I'm going to look at this component for this amount of time. One way to effectively choose what to focus your time on and how much time to spend on each component goes back to the threat modeling. Even if you can find vulnerabilities in some module, I'm not saying that's not useful, but it's going to be most useful to focus on the modules that you can already affect, the things that user input go to, right? If you find a vulnerability in a module that takes input from another module, and that module talks to another module, and you can talk to that, even if you find a vulnerability in that bottom module, you still need to chain the three together. That might be useful eventually. But if you want to find a vulnerability now, you do the threat modeling. You go, what inputs can I influence? You find where those go into the program, and that's where you start your focus.
That's interesting. So you kind of have to basically assume that there's going to be a multi-stage approach, and you can pick any one of these steps and say, well, if I find a problem there, then that's still a problem that should still be considered and fixed.
Right. Well, you can go top down and bottom up, right? Again, from the threat modeling thing, if you go where user input is, but also what is most catastrophic. So if there's another module that is writing physical memory directly, like that is going to give you probably the most power. Or in Linux binaries, if you have something that's making calls to system, right? Like, oh, that is also going to be very powerful. That's kind of what I would call bottom up, where you're looking for where you might have most impact. And top down would be where you're looking from where you can control from the user input. And then, of course, if you can get top down and bottom up, you can do it at the same time, right? And kind of find where they meet. That's probably your most likely path for success.
That's interesting. Okay, so a little bit more on the sentimental side. What keeps you working in security? What's motivating factor for you?
I enjoy it still. I think it's cool because even though I joke that I don't know how self-driving cars work, because I don't actually work on anything that routes the car or does collision detection or avoidance or anything like that. But I still get to work with really smart people who work on it. And I get to use the skills that I have, which are security related, to what I think is make a big impact, which is, ideally, if I do my job properly, because I'm doing it defensively, no one notices I'm there. But I know when I start working on a vehicle, I know just by virtue of looking at everything what the worst parts are, and I it feels really good to me when I know, like, oh, I remember this thing, like I hated this thing. This was really bad. Like we had SSH with the password you could type in, let's say, as a made-up example. And every time I close one of these things off, no one should notice because I've properly weaned people off of using it, let's say. But it does make the vehicle more secure. And then, so that's like from a impact and like doing good for the world. The other one is that I just think it's cool. Like I said, I still really enjoy reverse engineering, and I literally feel lucky when I have to reverse engineer something. It might not be the most effective use of time at all times, but something in me always finds it really interesting. And just by virtue of me working on lower level things, I do like some secure boot and things like that. Sometimes I have to bust open the debugger, and I always find that fun.
That's really cool. So the mission and the skill set is sort of enough motivation for you to, you know, put up with these really complex systems and spend a lot of time on it.
Yeah, absolutely. And I have a great team right now, and I'm motivated by people who work hard, who also have their own like intrinsic reasons.
Yeah, that's cool. So if you were to give an advice to someone who is just trying to break into this field or find their niche, what would that be?
So especially if they're all young, I would say don't focus too quickly. You have time to kind of play around and find what you like. If you're lucky enough to find something you're super passionate about, excellent, go for it. But at the same time, a lot of times you don't just find a passion. A passion evolves from getting good at something. So sometimes like I'm not passionate for hockey because I'm passionate for hockey. I'm not actually passionate for hockey either, but let's pretend I am.
But you're Canadian.
Sometimes
you have to be.
I am Canadian, so that's why I use that example. But let's say I just played hockey and I was extremely good, and you can derive a passion from that. So exploring around and finding what you're good at might actually help you discover your passion. But as you advance in your career, basically, you're probably going to want to specialize. And by having an early taste of everything, it'll be easier to kind of choose what you specialize in. I'll say that's number one. Number two, and like not to like say you have to put in a ton of time, but I would attribute more of me getting what was a dream job, even though I don't work there anymore, to my extracurricular work in security than to anything I did in college or at work. While I was working at Synac, I would go home and I would CTF for easily 12 hours a week, easily. And I'm not saying you to put an extra 12 hours a week, but I do attribute that extra time to both differentiating myself from others who are only like practicing a little bit and getting a skill that was super complementary. Another nice thing is that I was mostly doing development work at Synac. So I'm home and be like, oh, I don't want to program. That part of my brain was dead, but I still had energy for, let's say, reverse engineering or like figuring out exploits.
That's very cool. I don't know if I could possibly add anything to it. I think that you put it in a very beautiful way. Thank you very much for that. Thank you for your time. And it was great to have a conversation with you.
Yeah, it was great for me. Thanks for inviting me. I hope I was helpful.